In this section, we will discuss the derivatives and integrals of vector functions. The derivatives of a vector-valued function, r of t, is defined as in the case of a real-valued function. So, the derivative of r would be denoted by r prime, or equivalently, the derivative notation dr dt is said to be equal to the limit of the ratio as h approaches 0, as shown in the equation 4.2.1, provided the limit exists. The vector r prime of t is called the tangent vector, provided it exists and r prime of t is not equal to the 0 vector. The tangent line to the curve C at a point P is defined to be the line through P which is parallel to the tangent vector r prime of t. Let's consider the figure. We have a curve C defined by a vector-valued function. Now we consider a point P at some moment t, whose position vector is given by this vector function r at t. And some later moment, we consider a point Q obtained by replacing t by t of h to the position vector. We get the position vector OQ. Then the difference vector PQ is called the secant vector. Now, if we move the point Q to the point P, the vector PQ would become smaller and smaller, but the ratio of the difference with the quantity h would make the vector PQ to take the shape as shown by the pink vector. So the vector shown in pink is called the tangent vector. The tangent line to the curve C at the point P is defined to be the line through the point P parallel to the tangent vector, defined by r prime of t. Let's consider the following example. Here we have a two-dimensional vector function with the component functions as f of t and g of t, where f of t is defined to be equal to t squared and g of t equals to t. In some earlier section, we saw that the curve was being generated by the tip of the position vector of the point P at different moments. Now let's consider a particular moment when t equals 1. Then the x-coordinate of the point is given by f of 1, which is 1. And the y-coordinate is given by g of 1, which is equal to also 1. So the particle is located at the point with coordinates 1, 1. Now we consider a nearby point Q on the curve. Now if we connect the points P and Q with the origin, we obtain the position vectors of P and Q as shown. The vector PQ is called the difference vector. Now if we move the point Q toward the point P, then we see that the difference vector is getting smaller and smaller. Now, if we divide the difference vector PQ by the difference of the x coordinates of the points P and Q, we get this pink vector, which is called the secant vector. So as Q moves toward P, the limiting position of the secant vector is called the tangent vector, which is shown in this figure. The length of the tangent vector at different point are different, as it is clear from the definition of the tangent vector and also from this figure. If we divide the tangent vector by its magnitude, we get the unit tangent vector, whose direction changes from point to point, but not the magnitude. We will also have the occasion to consider the unit tangent vector, which is defined as shown in the equation 4.2.2. Namely, T of t equals r prime over the magnitude of the vector r prime. The vector T of t has magnitude equals to 1 for all t in the domain where the tangent vector exists. Hence the name unit tangent vector. Theorem: if R is a vector function with the component functions f, g, and h, where f, g, and h are differentiable functions, then the derivative of the vector function R, namely r prime, can be calculated by using either of these two formulas. Let's see the proof. We have the difference vector r of t plus h minus r of t is the vector with the components shown. Then, by the definition 4.2.1, we have the derivative, which can be written as the limit of the quantity shown here. Which can also be written in this form. Now, applying the limit to the vector shown here, we obtain this vector. Now, the first component here is exactly the definition of the derivative of the scalar function f. Similarly, the second component is the derivative of the second component function of r. And the third component here is the derivative of the third component of the vector function r. Therefore, we replace each limit by the derivatives f prime, g prime, h prime. This concludes the proof. We want to find the derivative of the vector function whose components are given here. And in the second part, we want to find the unit tangent vector at a given point, t equals pi. The derivative is given by the theorem 4.2.1. The derivative vector r prime has the components as the derivative of the component functions of the vector function r. Namely, the cosine t here would be replaced by its derivative, negative sine of t, and sine of t here would be replaced by cosine of t, and t would become simply 1 here. So r prime of t is equal to the negative sine of t I plus cosine of t j plus the k vector. Now to calculate the unit tangent vector at a given moment, from A we have r prime of pi equals negative j plus k, which is simply obtained by substituting the t value pi to this equation. We note that the tangent vector has the constant length, namely square root of 2. The unit tangent vector is then given by the equation 4.2.2. T of pi equals r prime of pi over the magnitude of that vector, which gives this vector.